Okay, if A changes after B, again 1 nanosecond, then when does x1 drop from 1 to 0? Nanosecond after B, which happens to be when A drops. Okay, that's our 1 nanosecond length. X2 is just a copy of B delayed by the propagation delay of that AND gate. So when does this drop? So it drops at the same time as x1. And then the inverse of that starts off low. And when does it go up? A second after x2, right? So there. And then x. Which is the exclusive OR of x1 and x3. And again, it starts off at 1. And then x1 is going to drop at that point. So a nanosecond later, the XOR will drop. And at this point, x3 goes to a 1, so you have a 1 and a 0, and that'll take a nanosecond for that 1 to propagate. So this goes low for 1 nanosecond, and goes up high. Okay, so that's the behavior of the circuit in those two cases. Again, in both cases, A and B are low, X is supposed to be 1. In that case, you get a glitch that's 2 nanoseconds long. In this case, you get a glitch that's 1 nanosecond long. Okay, depending on the order in which A and B change. All right? We good with this? Okay. And I'll probably have you do something like this on the midterm. Go through K-maps.
The coverage on there, you said that some of my, I could have had more coverage on there.
Yeah.
So I looked at them again, I could see like on one of them there was like a center square that I could have done. Helena was saying that the logic is different, so it does matter how much you're covering. I mean, it is really important to really get.
Yeah, you want to try to get as big a cover as you can. Now, there may be different ways that you can cover it and end up with equally good solutions that are different from one another.
So there is a right and a wrong way of doing it then?
Well, there may be more than one right way. Okay? Because all you have to do is make sure you cover everything. And you're allowed to cover things more than once. And you're allowed to cover don't cares. And so I think you can end up with a minimal cover is the one that uses the smallest number of terms possible. And there may be more than one of those. I'd have to think about that. But I'm not sure that's actually unique. But you do want to try to get a minimal cover, okay, which means using rectangles that are as big as possible. So I think that might have been one of the segments. So something like this, I mean, you need to cover the ones, that's all you're required to do. And it kind of helps maybe to start off with the outliers. So this one here kind of looks like it's by itself. Okay, it's only got a 1 next to it, and it's got some don't cares below it. And if you include this, you can cover both of those ones at one shot. Okay, so you want to try to cover both of those. You've got some don't cares down here. And if you go ahead and throw those in, you'll get a bigger rectangle, smaller number of gates that you need to use. Okay.
Why do you need bigger? You can't cover just 2.
You can cover just 2, but remember what we're going to do is we're going to change these into W, X, Y, Z. We're going to look at what we use to cover it, and we're going to write an equation that corresponds to it. So if I had covered it with just these, what would the equation be for that?
Not W,
Right.
X,
And
and
not Y.
not, yeah, not Y.
Right. So at every point in this rectangle, W is 0. Okay, so not 0, not W. X is 1, so that's X. And Y is 0, so that's Y bar. Z takes on the value 0, 1. Okay, so we have a term containing 3 variables. Okay, that's going to be a 3-input AND gate that we need to implement it. Now if we covered 4 of these, not W can have either 0 or 1, and we're still inside this rectangle, so we don't need the W term anymore. All we need is X to be equal to 1, and for Y to be equal to 0. Okay, that's a smaller expression. We've used the fact that if X is 1 and Y is 0, we don't care if W is a 0 or a 1. Okay, if it's a 1, it just puts us into these cases where we didn't care what the output was. So we can ignore that term. So we have a simpler representation. Okay, so the size of the rectangle corresponds to how many things you have to put in your AND gate. And the number of rectangles, that's how many things you OR together in the end. So if we use big rectangles, we'll get smaller terms, and we'll likely get fewer rectangles that we need also. So you try to cover as much as possible. Okay, so that would be the cover I would use for those. And then, what about this one?
W,
No.
Oh, we can do the switch around on the side, okay.
Yeah,
the one
we
in one.
could cover it like this, or we could cover it like this.
Or you could,
But you wouldn't
cover
do
it.
both?
or you could cover
Or you
it.
could just use
Just
a
one
2
or
by
the other.
2.
If you cover it like this, then you've absorbed this term also, which is good. You're trying to get as many ones covered as you can, because you want to use as few rectangles as
Yeah,
possible.
But you can use,
You could
you
drop
can
it down
do
by one.
Y not Z too,
Y not Z?
all the way down. Y not Z, right?
To cover this one?
It's
No,
0.
Y,
Make it a 2 by 2 box.
the Y not Z.
Yeah.
The
Oh,
left
that's
and one
right.
under it and an upper right one.
Let's see.
All of Y not Z, all the way
Fourth column.
down, the column, Y not Z.
4th column.
Right?
No,
Can't you do the whole thing?
they're
Here.
really,
Well,
I know, they could, like Murray was saying.
I don't.
That would work.
But can't you do this though?
Sure, yeah, you
Do
can
that
definitely do
too,
that. Right,
Y not Z?
definitely.
But then you would be taking into consideration this and this too?
No,
Well, that would give you a cover of this one and this one. You still need to cover this somehow.
So, but you can't do this as
But you
well?
could do that, yeah, definitely.
Okay.
all 4 in one.
you could just put all 4 in one box.
Yeah.
This
Wrap
one
around.
here and this one here?
Yeah.
It's in that box, but you can wrap around.
But you,
But you got 2 rectangles.
That's one rectangle.
Which-
That'd be one rectangle. Because you can wrap around.
oh yeah, if you just did this and this, so like
Right.
this,
Right.
Yeah, yeah.
Okay, yeah, that's the
then
way
you
to
wouldn't
do it.
have to worry about
Crazy.
all of
Perfect.
this then?
Mhm. Right, okay, good. That's the way to do it. So wrap that.
Just
Start circling everything.
Yeah, circle everything.
When in doubt.
Okay, yeah, so that was a good example. So you need to look at it and they can be sneaky.
It does still work if you do smaller boxes.
Sure, it still works with smaller boxes. It's just not as, the terminology would be it's not as minimal of a solution. Okay, minimal meaning how many 8s do you need? In the extreme case, okay, you can cover this with a single rectangle. And so W is 0, X can be 0 or 1, Y is 0, and Z can be 0 or 1. Okay, that's one way to cover it. If you wanted to, you could cover this with 4 rectangles. Okay, and you would get W bar, X bar, Y bar, Z bar, or W bar, X bar, Y bar, Z, or W bar, X, Y bar, Z bar, or W bar, X, Y bar, Z. Okay, logically it's exactly the same thing. Well, it's not exactly the same thing, but it's going to give you the same pattern of 1s and 0s. Okay, this is your original sum of products that we first did from a truth table, where we just found the product that corresponded to each row, and then we ORed them all together. This is what you would write just from inspecting a truth table and writing down the expression for each of the points where your output column is a 1. Okay, so you can get that from there, but the more coverings you do with your rectangles, the smaller your solution. This is going to take a single AND gate to implement. This is going to take 4 AND gates, each with 4 inputs, and it's going to take a 4 input OR gate. So it's a lot more transistors. Okay, it's also going to be slower because you're going to have 2 levels of logic. You're going to have a series of ANDs, and then you're going to have an OR. Whereas a minimal solution is just 1 gate, so less propagation delay.
Do you go to the next page?
Yeah. All right. If you have questions on your homework, if there's other examples where I said you could get a more minimal covering and you don't see it, let me know, and we can go over it. Okay, also make sure you include your don't cares. Same reason, if you have don't cares, you can get bigger rectangles. Don't waste rectangles covering don't cares if you don't care about them. So don't add extra rectangles because those are more expressions in your final answer. But if there's a way to, if you didn't have these over here, go ahead and cover those ones with a big rectangle like that instead of just the 2 of them. You'll get a smaller term. Yeah?
So what if there was a 1 on the bottom 2? So bottom left and then right to the right of that?
Here?
Yeah, right there. If there are 2 1s right there, would it be a smart idea? No, that would stay don't care.
Okay.
Would it be a smart idea to circle that entire bottom 2 rows? If
Oh, yeah, huh.
If there are don't cares around.
Because you have 2, right there would be a 1, where that 0 is,
If this was
bottom.
a 1?
yeah, if that was a 1.
So
Yeah.
then, those 2 bottom rows, would you do all of that?
Yeah, I would do all of those.
Okay. Because I wasn't sure if it would be better to just circle the 2 1s or to include all the don't cares as well.
If you include if you have a rectangle that's just 1 by 1, gonna have 4 terms in it that are ANDed. Okay, if it's a rectangle covering 2 squares, you're only gonna need 3 terms. If it's got 4 squares, you're only gonna need 2 terms, and if it's got, I messed that up. Okay, the more squares you cover with your rectangle, the fewer number of terms you need in your logical expression. So if you include all 8 of these, W would have to be 1, X wouldn't matter, Y wouldn't matter, and Z wouldn't matter. So this coverage right here, that's just W. Okay, you don't even need any logic.
Okay, thank you.
Let's see. So wraparounds are important. Another one, if this is a 1 down here, you can have this weird shaped rectangle like that, where all the corners are wrapped around. Okay, that's a tricky one, but it's perfectly valid.
How'd you write that one?
This one, let's see. So what's W? W doesn't matter. X doesn't matter.
That's
Y
always 0, isn't it?
Yeah.
So, yeah, so
Yeah,
not
X is
X.
0. So X bar. Right, and Y doesn't matter. It can be 0 or 1. Z has to be 0. So that's X bar, Z bar. And one other thing I saw, just something to keep in mind in general. If you write something like X bar, Z bar, make sure it doesn't look like this. Okay, those are different expressions. Okay, if you look at De Morgan's, this is actually equal to X bar ORed with Z bar. Okay, it's completely different from this. So make sure there's a space in your bars above those variables. Okay, did anybody solve the halting problem? Anybody go home and try it? If someone tells you it's impossible to write a program to do X, you should always go off and try it. You never know. I'm not sure I believe that it's unsolvable. You can actually have a copy of Earl's original proof on reliability. Trying to get through it, it's like really, you have to change your brain thinking to understand it. I mean, it's just a weird way of looking at things, but I'm not convinced it's actually unsolvable. It bothers me. So when I mentioned the talk I was doing in Portland State in November, and you asked me how to implement, how to build these things, I mentioned BEMS, micro-electromechanical systems. I just wanted to show you a couple of slides on those. First of all, these are being used today. If you drive a car with airbags, there's a MEMS system inside. They use them as accelerometers because they're extremely stable and they're extremely fast responding. So when you're in an impact and you get this sudden deceleration, there's a small circuit in there that's mechanical in nature and is detecting this sudden movement, and that's what triggers the airbag explosion. So these are actually things that are being used in our daily life. There's also interesting ideas out there, for example, building small robots that can be injected into your bloodstream to go through and like clean off the plaque on the inside of your arteries to reboot you.
Did you just say that's something that's real?
That is not real yet,
I was gonna say.
but there's things that are getting pretty close. I mean, that kind of thing is feasible at this point. It's just from an engineering perspective and a medical perspective, it's a long ways off, but it's feasible.
That would be hard to do with the regulations on that.
Yeah.
Because they
Foresight Institute that if you're interested in nanotechnology and future things, go look them up. And one of the things they've been doing for years is they had a ethics panel that had all these requirements, what you could or couldn't do. So they were proposing limits on like self-replicating circuitry or how things could be powered. What the failure modes for certain things were if the programming became corrupted, using coding so that if a bit got toggled somewhere in its memory, it would become non-viable, things like that. The Foresight Institute was started by Eric Drexler, an early proponent of nanotechnology back in the 80s. And it was a way to sort of prepare the world for this coming era. And this is nanotechnology in the version of manipulating matter atom by atom. Okay, so nanotechnology has become a buzzword. It's a marketing term. But there are people who are working on building these very, very small machines, much smaller than the mechanical systems that we have today. And Eric Drexler has started this institute to try to get us ready for when that becomes feasible. And so they do some interesting work. The other person that's fun to look at is Ray Kurzweil. You ever heard of him?
He is insane. I'm sorry, I can't stand that guy.
Yeah. Go look him up. He's the other end of the extreme. He believes in human augmentation through cybernetics and things like that. And he hopes to live forever. So he's trying
He
to...
literally takes like 80 vitamin pills a day.
Yeah, he's trying to live long enough to get to the point where we're able to sort of take our consciousness and put it inside machines. And he wants to be alive at that point so that he can live beyond it. I was in a talk that he gave one time, and it was like really interesting watching audience reaction while he was talking. The talk ended, and like all these reporters ran out to the payphones and started calling him. So it was pretty cool. So MEM systems. This was I don't know what this does. It's some kind of small mechanical latch, and it's on the order of microns. Okay, I mean the thing is absolutely tiny. It was built by Sandia Labs. They do a lot of this research. This is old. Okay, I'm sure this stuff is much more advanced than this now. But it's mechanical. Okay, it's not digital. It's not electronic. It's a mechanical system with gears and linkages and levers and things like that. This is one of those famous pictures I alluded to last time. That's an ant holding a micro gear. So extremely small scale. This is a combination lock that's mechanical in nature, and when they took the picture, there was a dust mite crawling on it. Right, dust mites are those like microscopically small things in your sofa and your pillows that eat dead skin. You don't even know they're there. So I mean, the level of manufacturing we've gotten to is pretty advanced already.
That's one G.
Yeah. And this thing works, the combination lock. It's pretty cool stuff.
Well, it didn't until he got to it.
Well, yeah. Okay, so we're going to continue with arithmetic, and we're actually like way ahead of schedule, so it's good that we have some other things to talk about here. But we're going to continue with arithmetic today and probably through Thursday. Looking at arithmetic operations and binary and looking at hardware for doing these operations, and that's going to take us deeper into some computer architecture ideas. So some sort of terminology and conventions up front. So we've talked about bits. Bits are binary digits, okay? They're a 1 or a 0, typically. And we don't usually deal a lot with just individual bits. We usually deal with groups of bits. So the most common thing we'll deal with is a byte. So 8 bits makes a byte. Okay, that's a pretty standard definition. You don't hear it as much, but a nibble is half a byte. Okay, 4 bits. So that's a nibble. That's a nibble. We'll see what we use those for in a bit. And then you hear about words, and words depend on sort of the context. Okay, if you're working on a 16-bit processor, a word is probably going to be 16 bits. Okay, if you're working on a 32-bit Pentium, the word is probably 32 bits. Okay, but it's not a strictly defined term. It really depends on the architecture you're working with. But it's sort of the most common chunk size of bits that you work with in your system. More and more words tend to be 32 bits because most processors are 32-bit processors. That's changing quickly. And then there's two special bits. The one on the left and the one on the right. So the one on the right is called the least significant bit. Okay, least. And MSB is the most significant bit. And if you think about how you count with these things, if you have a number and you change this bit, your number changes by 1. Okay, so that's the sense in which it's least significant. This bit over here, this is the 128th column, so if you change this one bit, your number changes by 128. Okay, so extremely significant. So MSB and LSB are standard terms. And typically, if you were to number these, this would be bit 0, and this would be bit 7. Now, there's places where this gets reversed, and that gets into like some political wars, but for the most part, bit 0 is the least significant bit, 7 is the most significant bit, and we'll try to stick to that in here. Okay, if it's a 32-bit, then it would be bit 31. That's the most significant. So that's just sort of convention, but it's easier if we nail that down to be able to talk about these things going forward. Okay, we can do logical operations on strings of bits, and when we perform them on each pair of bit, we call that a bitwise operation. Okay, so normally when we've been talking about ands, we're thinking of two logical values, and if they're both true, then the result is true. In a bitwise logical operation, you're performing this on pairs of bits. So the two least significant bits in these two numbers are 0 and 0. When we AND those, we get 0. So the bitwise AND starts with a 0. The bitwise OR also starts with a 0. The second bit is a 1 and a 0. If we AND those, we get a 0. But if we OR them, we get a 1. And so if you do this bit by bit, you can get the result of a bitwise AND and the result of a bitwise OR. And in programming languages, you usually have to specify which kind of AND or OR you want to do. Do you want it to be bitwise, or do you want it to be logical? Okay, logical says if they're both true, then the AND is true. Bitwise says bit by bit. If 2 bits are 1, the output bit is a 1. And the main reason we like to do this is the idea of a bit mask. So when I mentioned registers, I said, for example, one type of register is a status register. So inside your CPU, there's a register that has a bunch of 1s and 0s, and each bit means something. This bit means that the last operation you did resulted in a 0. This bit means that the power has failed. There's all these different status bits. So maybe your 4th bit from the right is an overflow bit. It says you tried to add 2 numbers and the result was too big. And so you've done an addition and you want to know, was there an overflow? So what you can do is you can create this special pattern of 1s and 0s with a 1 in that 4th bit position. That's called a bit mask. And if you AND this with your original number, your status register, what you get is something with 0s everywhere except that 4th bit. And something ANDed with 1 is just what you started with, right? X ANDed with 1 is X. So you get a number that's 0 everywhere except for that 4th bit, which comes from the status bit. And so now all you have to do is look at this resulting number and see if it's equal to 0. And in this case, the 4th status bit was a 1, and so this is non-zero. And you can say, there was an overflow condition. If that overflow bit had been cleared, if it was a 0 originally, then when you do this AND, you get a 0 out, and you can look at that and say, oh, the bitwise AND is 0, the overflow flag was not set. Okay, so it's an easy way to pull off an individual bit or a set of bits and tell if they were equal to 0 or not. bitwise ANDs are used to pick out individual bits from a variable or from a register. If you use a bitwise OR, you can set bits in a register. So if you wanted to set an overflow bit, for example, in this status register that has all these other ones and zeros, all you want to do is turn on this one bit, but you just OR it with that same bit mask. And when you OR with a 0, you don't change the value. X OR with 0 is just X. X OR, not X OR. So all of these bits are exactly the same as they were, but this bit is set to a 1. So you can use OR bit masks, ORs with a bit mask to set bits. Okay, and you can use ANDs to clear bits. So if I wanted to clear that fourth bit, I can AND it with a mask containing all 1s and a 0 here. Okay, X ANDed with 1 is just X. So these bits don't change value, but X ANDed with 0 is 0, so I've cleared that bit. So these are useful operations for manipulating registers that contain different flags and different indications of conditions inside a computer, for example. Okay, if you use an XOR, you can toggle a bit. So X XOR with 0 is just X. X XOR with 1 gives you the inverse of X. So here I set the fourth bit to a 1, and that will toggle the fourth bit of my original register. Okay, you get good at those after you do them enough. Because it's the same thing. You get to a point where you don't really have to think about it. I use the term bit flipping, that kind of thing. So those are useful tools to have. Another thing you can do is you can shift or rotate strings of bits. So on this one. So here's an 8-bit number. If you want to shift it left 1 bit, well, it's exactly what you would think. You just move everything over. You ignore this top bit, which gets shifted out, and we're just going to assume you're shifting it as 0. Okay, so it just takes this number and moves all the bits over one position. Bit 6 becomes bit 7, bit 2 becomes bit 3, and so on. When you shift left by 2, that's also the same as when you shift left 1 bit, that's the same as multiplying by 2. Okay, you can work through the math for that, but since everything is 2 and 0, 2 and 1, 2 and 2. Since our numbers are just weighted sums of these different constants, if you take what was here and use that to multiply by 2 to the 1 instead of 2 to the 0, you just double that component of your number.
So are you, that 0 that was on the left one at the top, are you putting it at the
It just
front?
disappears.
Or okay.
Yeah. Now if you do a rotate left, this will be okay, a rotate saves that bit that comes off the end and puts that back in the beginning. Okay, and a rotate is different from a multiply. It doesn't just multiply it by 2, it's doing something different. But it can be a useful way to take bits that have certain meanings in your number and move them to one end of the register. Okay, and you can do things to the right also. There's a right shift and there's a right rotate. When you do a right shift, it's roughly dividing by 2, but you lose a little bit of precision if you do a right shift. Okay, it looks like that. This 1 gets lost. So you're kind of dividing by 2, but you're also rounding sometimes. This was basically an odd number, and so when you divide by 2, there's an extra fraction at the end that you can't represent, so that's where that 1 goes. Okay, so those are just other operations you perform, shifts and rotates, as well as bitwise logic.
So it's integer division, yeah?
Yeah. And we'll talk about another version of right shift in a little bit on Thursday when we talk about negatives. So, okay, that's probably a good place to stop. We'll get back to this on Thursday, and I'll tell you about Tuesday's complement, which I didn't tell you about today. Exams on Thursday, Tuesday, we're gonna have. So, I'll do that here.
And I did plan.
Hopefully it's not too bad. Hopefully I can that's good, but it's very entertaining.
Okay.
Extraneous
Yeah.
circumstances.
Yeah.
Oh my.
Yeah, I want to do equations for all of them, but then just the circuitry.
Oh, okay.
Is that okay?
I like 1 to 0. They're easy. They're just 1.
It gets harder when you and 2, 3. Just 1 and 0. That's what you mean, man.
I don't know if I can do.
I'm sitting there. You're where I want to.
Oh, yeah. We have no spots. Right, those ones are just cool people. Hey.
Where am I?
I go back there. We
I thought you like, well, you go back up there. I'm back.
Everyone seats there.
Yeah, do what I want.
I must go up. I do whatever I like, Virgin.
No. Like, what's up?
Yeah. What? Forever. Oh, yes. I forgot it goes one of you. Yeah. I kept turning. Since like month. Since like last week. I didn't go when? This morning? No. Oh.